All right, next example, example 4. This example is very similar to example 2 that we've done in the previous video. Example 4, an island that's 3 miles off the coast, sorry, not 3 miles, 3 kilometers. So here's our island. And it's 3 miles off the coast. So this is the shore or the coast. And we're 3 kilometers off of that. Needs to be connected to the nearest shoreside city's data center. So the city lies 20 kilometers due east of the island. So here's our city. And we need to decide when we lay the cable, the fiber optic cable, are we going to go straight line to the coast and then straight to the city? Are we going to go all underwater towards the city? Or are we going to spend a little bit amount of distance going underwater and then connecting to the city? So let's just say that we go X miles inland to our attachment point, and then we'll run the cable underground the rest of the way to the city. So that means this amount of distance is x squared plus 9, and this distance, if the city lies 20 kilometers due east from the island, then this would be 20 minus x. Now what's the cost? The cost underwater would be, now they give it to us in cost of dollars per meter. So again, $1 per meter is just $1,000 per kilometer. So this would be underwater at a rate of $1,000 per kilometer. And then over here for underground, this would be, oh, sorry, I did that backwards. This is our underground rate. Our underwater rate is $3,000 per kilometer. Okay. So very similar. Our goal here is to minimize cost. So to minimize cost, we're going to construct a cost function where the distance we travel inland before connecting, that is our variable x. So we're going to travel this distance, and then that's kilometers. So then 3,000 times that distance would be the cost for that portion. And then this distance, 20 minus x times 1,000, would give us the other portion of the cost. 4, this can be a closed interval. The smallest x can be is 0. The largest it can be is 20. So now we've got a function and a domain. We could find critical points, which would end up being, if I do our derivative, this would be 3,000 x over the square root of x squared plus 9 minus 1,000. We're at the point in the semester where I'm not showing nearly as much steps for the derivatives because we are now doing a word problem. These problems get very lengthy and these videos get a lot longer if I show every single step. If you want more detail, of course, you can follow along in the notes that I have on D2L where I do show those steps mostly out. So now we have that. Again, the only place a critical point is a location where the derivative either does not exist or equals 0. This always exists because we never divide by 0 because x squared plus 9 never equals 0. So we only need to worry about when the derivative equals 0. That happens when x is equal to plus or minus 3 over 2 root 2, if you solve that. And again, since x represents a distance, this x is not going to be negative, so we'll just ignore the extraneous negative solution and take x equals 3 over 2 root 2 as our critical point. So now we want to compare values. So we'll plug in 0 into the cost function, we'll plug in 20 into the cost function, and we'll plug in 3 over 2 root 2 into the cost function. When you plug in 0, we get $29,000. When we plug in 20, so this scenario here, when C is 0, this is going straight to the shore, then to the city. This is not going underground at all, just going directly all through, all underwater to the city. This ends up being, the cost is, I'll write it as a decimal first. This is, or excuse me, I'll write this as a, actually I won't even bother. I'll just write you the, I'll just round it. Decimal's kind of gross. This is $60,000 and $671. Sorry, $60,671. I rounded to the nearest dollar. And then this one, when we plug it all in, we get $28,485. So clearly this is the minimum. So lay cable underwater to a point 3 over 2 root 2, which is approximately 1.06 kilometers due east on the shore, then continue underground. And that is the most economical way to lay that cable.